So we have Euler's method here, and we are given a graph here. Okay, so that is the function dy over dx. It's the function of x and y, and we are always given our initial y. So here, our equation, we are given the initial y, and what we want to find would be the x right here, or yi plus 1 rather. So our yi plus 1 equals yi plus the function of our xi and our yi times our step size h, where our step size equals to xi plus 1 minus xi. So we are given an equation for our example 2e raised to negative x minus 0.2y, and we are given our first y, which is 4, and our step size is 3. So let us go directly. That will be our main equation. So we are going to substitute first our given to our main equation. So we have 4 plus our 2e raised to negative 0, since our x is given and it is 0, minus 0.2 times 4 times our step size 3, and we get 7.6. So for our y3, or our second iteration, we substitute 3 as our x and our new y, 7.6. We will have the value of 3.3387. So still it's far from our true value, so we are going to proceed to our y6, or our iteration number 2. So we have the new value of y, and our value of x is 6. Okay, so we multiply that to our step size 3. And we have 1.3504. So that is closest to our true value, which is, I think, 1.2. So our error for that is given by 1.2 minus 1.3504 over 1.2 times 100, and that will be, let's calculate that. Okay, so we have 12.53%. That will be all for our Euler's method. So we go directly to our midpoint method, where we're also given dy over dx and the function of x and y. They are given the initial y and initial x, that would be y naught. So we have k1 here, which is the function of xi, yi, and we have k2 here, a function of xi plus 1/2 h and yi plus 1/2 k1h. So we go directly to our example. Oh, just a reminder, guys, because we have this rule in ODE wherein we cannot solve the given equation if it is not in the form of dy over dx equals our function. So our first iteration right here, we are solving for k1, and we got 1.2, which is our true value, and we go directly to our k2, where we substitute our x and y and our k1. So we multiply that by 3, step size is 3, and the function of 1.5 and 5.8. So our k2 would be negative value of 0.7137. So we directly substitute those values to our yi plus 1. So this would be 1.8589. So you can see that it is still far from our true value, which is 1.2. So we go directly to our iteration number 1. So we solve for our k1, given the new x and the new y. So since our step size is 3, that will be 3 for our x, and the y would be the new y for 1.8589. Okay, so we will have the value of negative 0.2722. And to solve for our k2, we just substitute our x and y and our k1, so that we would have negative 2679. Sorry for that. So we go directly to our yi plus 1, then 1.8589 plus the negative of 0.2679 times our step size 3, and that will be 1.0552. So that is closest to our true value, which is 1.2. So that's it. So still in our ODE, Ralston method, where dy over dx is equal to the function of x and y, and we are given the initial x and y, and we are given k1 same as before, k2 that will be the function of xi plus 3/4 h and yi plus 3/4 k1h, and that will be our yi plus 1. So like the other methods in ODE, we have to remember that we can only solve our equation if it is in the form of dy over dx. So that will be the very first step, or the very first thing that we should do in solving our ODE method. So we solve for our k1, which is equal to 1.2, just like the others. And for our k2 would be the function of 0 plus 3/4 times our step size 3, and our y as 4 plus 3/4 over 1.2 times our step size 3. So we have the function of 2.25 and function of 6.7, and we substitute those to our given equation, and we have the k2 of negative 1.1292. So we substitute those values for our yi plus 1, and we will have the answer of 2.9416. Oh, that is relatively far from our true value, so we proceed to iteration number 1. So we still get our k1, which is the function of xi and yi. Our new x will be negative 3, and our new y will be 2.9416. Okay, so what will we have here? Negative 0.4887, and we solve for our k2, 3 plus 3/4 of our step size 3, and 2.9416 plus 3/4 of our k1 times our step size, which is 3. Okay, so we have the function of 5.25 there, and the function of 1.8420. So we have a k2 of negative 0.3579, and we substitute those to our yi plus 1. Okay. So you can see that these methods are only formula based, which is very easy for us to understand, because it's just about substituting the values after we get them, and we will get the final answer. So we could see that every method is taking how many iterations to get close to our true value. So okay, from 2.9416 down to 1.7371, and that's it. Still in our ODE section, so we have next Yoon's method. Okay, same for k1, the function of xi and yi. For k2, we have the function of xi plus the step size, and the yi plus k1 times the step size, and we have yi plus 1 right there. Yes, that's it. So we solve also the same equation as the given equations for our previous methods. So we have also y equals 4 and our step size is 3. So our k1 would be 1.2 still. because all of these methods have the same formula for our K1. For our K2, we have a function of 3 and our 8.1, 8.2, sorry. So our K2 will be negative 1.54. And that's it. So for our yi plus 1, we have the 4 plus the 1/2 of our 1.2 plus the 1/2 of our negative 1.5404 times our step size 3, and we have 3.4894. So wow, that is really far from our true value. So we proceed to our iteration number 1. Hope we could get closer to the true value, which is 1.2. So cross your fingers, guys, and get ready. So we have a K1 of negative 0.5983, and our K2 would be the function of 6 and the function of 1.6945, and we have negative 0.33, what was that? 3339. Okay, so we have here our yi plus 1. Let's hope that it will be closer to our true value. Okay, times 3. The answer will be 2.0911. Okay, for our Yun's method, that will be it. And we have the RK4 method, our last method for our ODE, but certainly not the least. So we have here K1, K2, K3, and K4. That will be our equations for the RK4 method, or the Runge-Kutta fourth order. So our yi plus 1 would be yi plus 1, 6 times K1 plus 2K2 plus 2K3 plus K4 times our step size h. So just like our previous methods, we would have the same equation, and still, guys, please still remember that we can only solve the ODE when it is in the form of dy over dx. Okay, so we have our K1 still 1.2, and our K2 would be the function of 0 plus 1/2 times 3 and 4 plus 1/2 times our K1 and our step size 3. The function of 1.5 and the function of 5.8 gave the answer of negative 0.7137. So our K3 would be the function of 0 plus 1/2 times 3 and the 4 plus 1/2 times our K2 times our step size 3. And the answer for K3 would be the function of 1.57 and the function of 2.925. So we have negative value of 0.1396. Okay, so we have K4 right there, and we will solve for that. Okay, times step size 3. Let's calculate that in a bit. That's the function of 3 and 3.58. And we have a negative value of 0.6167. So we substitute those k's to our equation to get our yi plus 1. So this will be easy. So remember, we have 3 over 6 there, where 3 is our step size h. And we have the yi plus 1 as 3.4384. So guys, you can see which method in this ODE form is the best method to use, where we can get closer to the true value in just few iterations. Somehow all of them would bring us to the true value, but it would take us a lot of iterations and time to do so. So after seeing this video, our tutorial for our ODE, well, you guys can tell which method would be best to use to get to our true value as fast as we could, lesser iterations, and that will be the end.